Our topic today is polarity. What we're going to be discussing is what is it that makes one molecule polar and another molecule non-polar. And of course, polar means that there is a positive region, positively charged region to the molecule, and a negatively charged region to the molecule. It's polar. It has two poles, positive and negative. And then we will discuss further, not in this lesson, so what? Who cares if a molecule is polar? What does that have to do with anything? And you will see that it actually gives a molecule a lot of different characteristics, being polar or not. Okay, so the first thing is that if a molecule doesn't have any polar bonds, it will be a nonpolar molecule. It's as simple as that. So, for instance, methane if we talk about the bonds between carbon and hydrogen, what we know is that the difference in electronegativities between these two elements is less than 0.5. So essentially, they are sharing electrons equally. So none of these bonds are polar because there's not that great of a difference in electronegativity. And so if none of the bonds are polar, then that means that we don't have any electropositive, electronegative regions to this molecule. So the whole thing is going to be nonpolar in this case. Okay, no polar bonds, then the thing is not going to be polar. Molecules that do have polar bonds may or may not exhibit overall polarity. It depends. So if the polar bonds are there, if the difference in electronegativity between two bonded atoms is greater than 0.5, that molecule might be an overall polar molecule, or it might not. So how do we know? We have to look at their shape. So shape determines whether a molecule with polar bonds is itself polar. And I will explain this ad nauseum in a few moments. So it's shape that determines this. So let's have a little jargon here. Molecules that are polar can be referred to as being dipolar, which is kind of redundant, but dipolar, or to having a dipole moment. So a polar molecule can be referred to as being dipolar. Or if somebody asked you, does this particular molecule have a dipole moment? That would mean, is this molecule polar? The polar character of a molecule is represented by an arrow. This is electropositive, and the arrow points to the electronegative portion of the molecule. Okay, so let's look at a couple of molecules. HF, hydrofluoric acid is what this is, HF. It's a pretty simple molecule. And so the question we ask ourselves is, does do these two atoms have a difference in electronegativity that's greater than 0.5? Well, yes, in fact, they do. So that tells us hydrofluoric acid is a polar molecule. It's got a polar bond, and in this case, because there's just two atoms, we can say, yes, it's a polar molecule. And we would draw the arrow looking like this, knowing that this is the electropositive pole, this is the electronegative pole. How do I know that? Because fluorine has a greater electronegativity, so it's going to keep the shared electrons around it most often. Okay, now let's do something a little more complicated than just that. What about carbon dioxide? Okay, if we make a Lewis structure for carbon dioxide, what we will end up having is something like this. We've got two lone pairs here and here. What is the shape of this molecule? The shape of this molecule is linear. Okay, so everything is in a line on the same plane. Now let's look at where the electropositive and the electronegative regions are in this molecule. Oxygen has a greater electronegativity than carbon. So that means that for this particular bond, we're going to go like that. And for this bond, we're going to go like that. Okay, so here's the electropositive region of the molecule. This ligand is electronegative, and this ligand is electronegative. So now what we have to do is we need to think about where in three-dimensional space these poles kind of coalesce. So this is our electropositive pole, and that's that. Now because these things lay on the same plane, we have electronegative, we have electronegative. Okay, where does the electronegative meet, I guess, or intersect? So if we have electronegative, electronegative, the midpoint between those two is directly here, over the electropositive pole. And if the electronegative's midpoint is exactly in the same spot as the electropositive pole, then everything cancels out, and we say that this molecule is non-polar. It has no dipole moment. Even though it has polar bonds, the net result of this electronegative, because they coincide in exactly the same spot as the electropositive pole, is that everything cancels. So basically what we can think about is that in three-dimensional space, if the molecule is symmetrical, exactly symmetrical in the same plane, well, not exactly that. If the molecule is symmetrical, the poles are going to cancel, and the thing is going to be nonpolar, even if it has polar bonds. So we're going to get more and more complicated with this tomorrow. Tomorrow we're going to look at a tetrahedron, a pyramid, and bent. And then from there we'll move on to the shape table. And on the shape table we will categorize each of the shapes as being polar or nonpolar if they are containing polar bonds. Okay, so let's do one more example. Let's look at water. H2O. Okay, if we make a Lewis structure for water, it's going to look like this. And we know that these two lone pairs are going to do what to these pairs? Right, we're going to bend. So this thing is going to be bent. And I will show you an actual three-dimensional model of this tomorrow. Okay, now, the difference in electronegativity between these two is such that each of these bonds are polar bonds. The electronegative, electropositive, electronegative, electropositive. We could also write it like this. Here's the electropositive, here's the electropositive, and here's the electronegative pole. So the electronegative pole of this molecule is here, right on the oxygen. We've got an electropositive pole here, we have an electropositive pole here. Where do these two poles intersect? They intersect somewhere around here. Does this physically, in the three-dimensional world, does this spot lie directly over this spot? No, it lies just below this spot. So what that tells us then is that water is a polar molecule. Water has a dipole moment because its electronegative pole is here over the oxygen and its electropositive pole is somewhere here in space. They don't land here, they land here, their midpoint, not in the same spot. Okay, they are asymmetric around the oxygen. So we'll look at this in 3 dimensions tomorrow, and then again we will go over your shape table and classify each of those shapes as being polar or nonpolar if they contain polar bonds.